Welcome to the fascinating world of automata theory and compiler design. This course aims to introduce you to the fundamental concepts of formal languages, grammar, and automata theory. You'll also delve into language translation and compiler design, gaining practical skills essential for constructing a compiler. Our department is committed to providing high-quality computer engineering education infused with socio-moral values. We aim to offer state-of-the-art ICT-based teaching, groom students into professionally sound engineers, and ensure they become employable professionals with strong ethical foundations. Let's begin with the concept of alphabets in finite automata. An alphabet is a finite, non-empty set of symbols, such as letters or numbers. These symbols form the building blocks for creating strings and languages within automata theory. Strings are finite collections of symbols from an alphabet, and languages are collections of appropriate strings. Languages are defined using input sets, which are crucial for understanding how automata process information and generate outputs. Finite state machines are mathematical models that process inputs to produce outputs. They consist of intermediate states that help in designing programs like text editors and lexical analyzers, showcasing their practical applications in computing. Finite automata are defined using a five-tuple, which includes a finite set of states, input alphabets, and transition functions. These components work together to determine the next state, starting from an initial state and moving towards final states. The finite automata model is represented with input tapes and finite control. Each input symbol is placed in a cell, and the finite control decides the next state based on the input received, illustrating the systematic processing of information. Finite automata are categorized into deterministic and non-deterministic types. Understanding these types is crucial for grasping how different automata function and process inputs in varied ways. Deterministic finite automata have a single path for each input from one state to the next. This predictability makes them easier to understand and implement, as each state transition is clearly defined. Non-deterministic finite automata allow multiple paths for inputs, offering flexibility in state transitions. This characteristic can simplify the construction of automata, as it doesn't require specifying exact transitions for each input. Deterministic and non-deterministic finite automata differ in their approach to state transitions. DFAs have a single path for each input, while NFAs can have multiple paths, making them easier to construct but potentially more complex to analyze.